This lecture is going to be over section 18.1. We're going to get into the concept of electric potential energy. Now, if you remember back from chapter 7, which you may not, so it would be good to review because those are the concepts we're going to be going over. We're going to be taking a look at potential energy and work and force to kind of see how those same concepts, when we apply them to mechanical objects, can also be applied to electricity. And this is what we're going to be seeing here. We're going to take some of the more fundamental definitions that we had in chapter 17, and we're going to apply them here. So now we're going to try to rope these concepts together so that we can have a more robust fundamental view of how work and energy can apply not only in a mechanical sense, but also here in an electrical sense. So that's what we're going to be doing here. Now, the summary over this is going to be stated as follows. You see the picture here. We've got a point charge, and we've got point A here, and we've got point B here. This point charge just kind of exists out here. But as it exists, it's going to exert an electric field, and this charge is going to get caught up in that field. Now, how are we going to look at work in this particular context? Well, the work that's done by the electric field force on a charged particle that's moving in this field is going to be represented in terms of potential energy. What we're going to be looking at is describing the work as a change in the potential energy from point A to point B. This charge, particularly if it's positive here, it's a little easier to see. As it moves from A to B, you're going to see a loss of potential energy. And that is due to the work that's being done on this charge by that charge. That's what we're going to be doing here. So for a charge Q prime that undergoes a displacement S that's parallel to a uniform electric field, the change in the potential energy is going to be given by Q prime times E times S. Now, if you look at the expression right here, Q prime times E, that's a way of saying force. And if you'll remember back, the way we describe force for the purposes of work, we looked at force times distance. Well, this is going to be the same principle here. We're going to be looking at force times distance, and that description can also turns out to be equivalent to the change in potential energy from point A to point B. So the potential energy for point charge moving in a field produced by a charge at Q that is a distance r away is going to be this. That's how we describe the potential energy here, here, and here. So that's the general description of what's going on. So let's actually go to 18.1. Let's kind of take a look at the description here. So you can see here that the chapter is pulling the information from chapter 7, where the work on something that's going from point A to point B is going to be Fs cosine phi. This is going to tell you the amount of work that's done by this particular force as it's pushing an object S, and again, those are both vectors here, and so we're going to be looking at the angle in between them. So it's the distance between the force and the displacement. So we're also going to need to look at the fact that if the force is conservative, and the electric force happens to be, then the work done by the force can always be expressed in terms of the potential energy. So when a particle moves from a point where the potential is u sub A to a point where it's u sub B, then the work being done by that particular force is going to be the change in the potential energy, which we're going to represent with minus delta U. So note that the delta U is going to be the final potential energy minus the initial. So when this is positive, then that means the potential at A would be greater than what you would see at B. And the potential energy decreases because the final value is less than the initial value. So, similarly, the potential energy of a baseball decreases as it falls from a high point A to a low point B under the action of the Earth's gravity. So the force of gravity does positive work, and the gravitational potential energy decreases. That makes sense. It's closer to the Earth, so it's also in motion, so it's going to have less potential, or gravitational potential energy. So when a ball is thrown upwards, the gravitational force does negative work during the ascent, and the potential energy increases because it's higher above the Earth than what it used to be. So you can see the analogy here in figure 18.1b. It shows the analogous situations here. So you got the ball, it's falling, positive work is being done, and it is the same as minus the change in the gravitational potential energy, because as it falls from here to here, that actually decreases. Well, the amount of work being done is positive, so that's, you put the minus sign there, and that's how you arrange it to make it work. Now, electric and gravitational forces are considered to be conservative. So work done by either of those forces can be expressed in terms of the potential energy. So when you got a charge moving in a uniform electric field, that force of the electric field is Q times E, and that's where you're getting this particular value from. The work is going to be the same as the minus change in the potential energy, and it's going to be QE times S. So now the work energy theorem states that the change in the kinetic energy during any displacement is equal to the total work done on the particle. So if in equation 18.2, if that gives the total work, then the change in the kinetic energy from B to A is the same as the change in the potential from A to B. And if you change that around, basically what you get is the kinetic plus the potential that you had at the outset is going to be the same as the kinetic plus the potential that you had at the end. In other words, the total amount of energy here, if you're being acted on by conservative forces, it can change form from kinetic to potential, but you're always going to end up with the same sum. So let's look at an example here, figure 18.2. You've got a pair of charged parallel metal plates. They're set up, they have a uniform electric field that has a magnitude of E. The field exerts a downward force with magnitude of F is equal to Q prime times E on a positive test charge Q prime. And then as the charge moves a distance S from point A to point B, so that's its path. And you can see that drawn here. The force on the test charge is constant and independent of its location. In other words, it doesn't matter where it is. So the work done by the field is going to be F times S, or Q prime times E times S. And the electric force has only a Y component, up and down. So the work on it, the work that it does on the charge is independent of the path. It could make something real crazy here, but as long as it ends up, it starts at A and ends at B, doesn't matter how it gets there, this is the force that it's going to feel. So you can represent this work in terms of a potential energy, just like we did for gravitational potential energy. The Y component of the force is going to be equal to minus Q prime E, and that's going to be considered constant, no X or Z component. Work is going to be independent of the path the particle takes. So just as a potential energy is going to be minus mg, or the force due to gravity is going to be minus mg, and the potential is going to be mgy. The potential energy for the electric field is going to be represented in much the same fashion. Now, here we've chosen U to be a 0 at y is equal to 0, and when the test charge moves from y sub a to y sub b, the work done on the charge by the field is going to be given by this. So you can see the work being the change in the potential energy from A to B, and you can see the formulas written here, and you can see it condensedly written here. So when y sub a is greater than y sub b, then the particle moves in the same direction as the electric field. U decreases, and the field does positive work. That makes sense. When y sub a is less than y sub b, the particle moves in the opposite direction. moving back that way. U increases and the field does negative work. In particular, if you redefine them as S and 0 as far as your start and stops points, then this gives you equation 18.6, and that's in agreement with 18.4. So you can see the differences here. You can see as a positive charge, which you would expect moving from positive to negative, this would produce a force of Q prime times E, and then that information is turned back in here. If you've got a positive charge here that is being moved back towards this plate, then this is doing negative work, and then the potential energy increases because as the positive charge gets closer to these positive charges, it gets harder and harder for it to get closer because these are wanting to repel. So you can see here, if you replace that positive charge with a negative charge, it's going to move in the direction of E, and the field does negative work on the charge, and this potential energy increases, or I'm sorry, as it moves from this, if it moves in this direction. Sorry, apologies on that. And then if you have a situation here where you still have the same plates, you have a negative charge, it moves in this direction, the field does positive work, and U decreases. So depending on whether you've got a positive or a negative charge in between those two plates, you can see how the potential energy will increase or decrease depending on what scenario you go with. You've got some examples here. I will encourage you to go through and to look at those. Potential energy of point charges. It's useful to calculate the work done on a test charge Q prime when it moves in the electric field caused by a single stationary point charge Q. So suppose we place a charge Q at the origin of the coordinate system, and suppose the test charge Q moves along the x-axis from here to here. How much work does the force do to Q, or how much work does the force do to Q on Q prime does during this displacement? That's a mouthful, isn't it? Okay, so you got a test charge here, you've got a point charge here. You've got another charge over here that moves from A to B, and you are seeing here that the force on the test charge is a function of position. So you've got the position marked down here, you've got the force on it up here. The force is being described as formulas from chapter 17, if you remember those. It's being drawn like this, and then you're seeing the movement. You're seeing small movements here, delta x. Now, you can't just simply multiply the force by the displacement because the force is not constant. It's going to vary with x as you go through. So the work done on the test charge is represented graphically, as you see. In order to be able to actually produce the total amount of work, you're going to have to go through and you're going to have to use calculus. Now, this course is built to teach you physics without the introduction of calculus. So what we're going to end up saying here is that your result ends up being this. And equation 18.7 also shows how we can define a potential energy for this interaction. This definition is consistent with a requirement that work is defined in this manner. If both charges are positive and B is greater than A, then the electric field force on Q does positive work as it moves away from Q. Correspondingly, if U sub A is greater than U sub B, then the potential energy decreases, just as you would expect. So the important result is going to be generalized to the case where Q, point A, and point B don't all lie along the same line. It can be shown that the work done by Q prime by the field produced by Q is going to be the same for all possible paths, even though those paths of those points don't lie along the same radial line from charge Q. The work depends only on the distance A and B, not on the details. So if Q prime is returned to the starting point by a different path, the total work done in the round trip is going to be 0. In other words, if you take it from A to B and then back to A, the total amount of work is going to be the same. these are the needed characteristics for a conservative force field. In other words, thus we've verified that the force that Q exerts on Q prime is considered to be a conservative force. And we've got some other formulas here. The potential energy is defined in this fashion. Obviously, it's energy. We're going to be looking at joules here. So potential energy is always defined relative to some reference point at which the potential energy is zero. In equation 18.8, potential energy is zero when Q and Q prime are infinitely far apart. Therefore, U represents the work done on the test charge by the field of Q when Q prime moves from an initial distance r out to infinity. If they have the same sign, the interaction is repulsive and the work is positive, and U is positive at any finite separation. If they have opposite signs, then the interaction is attractive and U becomes negative. So we're going to generalize to situations in which the electric field is caused by several point charges, and these charges are at several different distances from our test charge here. From that, we're going to look at the vector sum of the fields due to the individual charges, and the total work is going to be the sum of the contributions of the individual charges. So we're going to use this particular formula to show the algebraic sum of the effect of all of these charges on Q. So we can represent any charge distribution as a collection of point charges. So equation 18.9 shows that we can always find a potential energy function for any static electric field. So it follows that every electric field due to the static charge distribution is a conservative force field. So that's a lot to take in for this particular section, but it's pretty important.